Alright, CrewtonRamone'sAwesomeAmount.com. Quick recap. Working with a student from last week. We were completing the square. And here's his notebook. A few errors in it, but overall quite excellent. We're an 11-year-old completing the square to solve for x. And let's see here. There's a little bit more of it where we fooled around talking about plus or minus why it is a negative times a negative is a positive. What happens with plus or minus and so forth, because we talked about the concept of when I take the square root over here, it's going to be plus or minus 3. And there we are with a completing the square, really simple, x squared, 2x and 1. It's the same thing as where we should have had an equal sign over here in a rectangle that's 3 by 3, but you know, he didn't finish drawing it. And then we can see that x plus 1 is the same thing as 3, and here's x plus 1 is the same thing as negative 3. And it's very simple to see what do I have to do, or just take away 1 from each side. And over here, I take away 1 from each side, but it can be confusing. So what I have here is 0, 0, which is a 1 and the negative 1. So then when I take away the positive 1 and the positive 1 from both sides, using my imagination in this case, I wind up with negative 4, because 1 minus 1, when I take off the positive 1, leaves me with the negative 1, and there's 3 other negative 1s over here, so you get negative 4. Anyway, the kid understands it. Simple, easy. Here's a couple other problems. Like I said, he was whipping through these, and then he comes back a week later, and I wasn't going to do this with him, but you'll see this is on the password protected screencast page if you want to see how to do these. We went through a simple one like this, where this was, and we had done a lot. By the time I figured out I should probably take my camera out and snap a couple pictures. This was x squared 10x plus 9, and I said, tell me what x is. Solve for x. And use completing the square, that thing we did last week. And he couldn't 100% remember how to do it, which is 100% natural and normal with kids, right? He's been in school all week and doing all kinds of other math, and he forgot what to do here. So we talked about, and he got the blocks out, and he knew he had to complete the square, but he kind of forgot that he had to get the 9 out of there and so on. So I helped him by subtracting 9 from both sides, just like we did a second ago. And then he remembered that he added 25, so he knew he definitely had to add 25 on this side. And he had the negative 9 blocks over here, so he combined his 25 and the negative 9, and he came up with 16. And he had a square over here that was x plus 5 by x plus 5, which you'd have to use your imagination. You've seen it enough times, though, I think, by now. If you haven't, check around on the blog or at my website. And we could see, and I put this on here for the benefit of the viewer, not for him, because he understood that if you have the square, we're just going to look at that one side, and you wind up with x. And this is supposed to be a 5, even though it looks kind of like a 3. It's still x plus 5. It's the same thing as plus or minus 4, right, because it's the 16 here. And note, teachers, that I use a nice perfect square with these kids to start off, right, until they get a feel for it. And just because they're 16 or 18 or 22 in college or 19 or whatever it is, doesn't mean that you can skip all the steps in the ladder. Go to the concepts page and see. You just keep basic, easy steps, and they can baby step their all the way through quadratics and into the calculus. Anyhow, so now we see x plus 5 is the same thing as 4. Okay, well that's easy, right? Negative 1. And then he did that without even subtracting from both sides. He just thought, well, that's easy, just take away 1, right? So x must be negative 1. And then x plus 5 is the same thing as negative 4, thought for a second, and did not use 0, 0 to take away 5 from both sides, right? Make a 0 here and take away 5 from over here to get 9. He just figured that negative 9 plus 5 is the same thing. So that's, again, you have to train them. You have to get them used to problem solving this way, where you use 0, 0, no fun, get back to 1. 0, 0, no fun, get back to 1 every time. If this was 2x plus 5, this is a hypothetical, then you'd have to use 0, 0 to get rid of this, and then divide by 2, or whatever it is, right? Okay, so then you can see we were building squares, we fooled around, did a bunch of other stuff here. And the other thing, too, is, we already did this last week. This is easy. I know how to do this. Then he couldn't remember how to do it. But it's like, this is lame. Let's do something else. Right, okay, fine. Let's do something else. We'll come back to this another day. So we fooled around with square numbers. And the way we did that, it was got him to build squares. There's a whole page on square numbers at Crewton Ramone's House of Math. But he was actually fooling around and kind of seeing if he could push any buttons on me and get in trouble. So he started building this, and I just kind of let him go. And then he started building that, and he goes, "I'm going to build the pyramids of Egypt." I said, "All right, build a pyramid from Egypt." And so he builds the 10 by 10. Then he's got a 9 by 9 there. And then he was going to grab 9/8, and then he realized that 9/8 wasn't going to fit on there very nicely. Ooh, so now he's got a square. And then he's got another square, and then pretty soon they're all squares. And by the time he got to the end of them, I went, so do you notice anything in common here? Do you see anything the same? He goes, yeah, I had to use all squares. I was wondering why you just let me build. I was like, yeah, because you can learn all kinds of stuff by just fooling around with blocks. So now, how many in this square? 100. How many in this square? 81. All right, let's get your pencil and paper out and start writing them. So, oops, we'll come back to this in a second. So, he writes out all his square numbers. Right? And there's his pyramid. There's a drawing of his pyramid, and he was actually going to try and fit them all in there. And then we fooled around making cubes. Saying, oh, this 14 is not 14, it's 1, 4. Right? It was going to be 9, 6, and he was going to write them out this way. I said, you know what, why don't you write them like this instead? And so here we see square numbers, x squared. All right, then we have cube numbers, but it's actually third power numbers. And if you've seen some of the other stuff on the blog and at the website, you see that we stay in 2 dimensions for x to the third. But it's 1. Oh my goodness. And then we made a cube with the 2's and got an 8, right? And then we made a cube, an actual 3-dimensional cube. We didn't stay in 2 dimensions, but just quickly talked about what if it was 3 by 3 by 3, since he had built a pyramid and we were in 3 dimensions. 27, right? And then, so look at all the math he had to do there to get this. And see, the kid gets some experience with what square numbers are, what they look like, what these numbers are here, what the symbols look like to represent square numbers, what the symbols look like to represent cubic numbers. And again, the grade school teachers that don't see the college textbooks and the high school textbooks because they spend all their time in teaching quote-unquote grade school math. We've got it segmented and the rules and process down for each year. I have now 14, 15, 16-year-old kids that have never seen the cubes. Right? So when they see a problem in an algebra textbook that's like, I don't know, 3 to the x equals 27. Well, they don't, it doesn't even dawn on them that the exponent would be 3. But how easy is it if you've seen these already? You already know, like, x to the third, or no, wait, yeah, x to the third is 729. What would that be? It would be 9. Right? They would have no idea how to even start figuring it out. What do I do? Well, you have to be able to take the cube root of 729. Well, how do I do that? Oh, jeez. Okay, so now we can go back and take a look at this. Well, he was figuring out, well, I have 144, and I have to multiply that 12 times to get 1728. And there it is, very simple, right? And look at him doing it the hard way, where he puts out 288 and then 1440 and then has to add them together. But anyway, I have a video on cross multiplication where you could do it all in one line and fasten your head, but we'll skip over that for right now. And again, just want to point out, there's his pyramid all busted up because he was playing Jenga with it. And even at 11 years old, the most fun part about building anything is knocking it down. Right? We're just playing around, doing math, having a good time, some math enrichment. So 1728, we spent a lot of time talking about that because that is 1 cubic foot in inches, right? There are 1,728 cubic inches in a cubic foot. And then we could talk about cubic yards and so on. But anyway, this is a definite measure, unit of measure in construction and so forth, a cubic foot. So seeing that 1728 is 12 times 12 times 12 in cubes. Then we fooled around, and I just want to talk about this really quickly. How is it possible that you can teach multiplication without teaching division? Just like, how do you teach addition without teaching subtraction? Right, combining the inverse functions. literally, you can have it so segmented and so into rules and process and so far away from concepts that kids can go a whole year and not understand the very simple concept that what we have here is a rectangle and the two sides. So here, and you'll see in a second, we're going to switch this around to make it fit with this. We have the area, one side, the other side, and the perimeter. And this is 100% for the benefit of the viewer, because this 11-year-old student was doing this all in his head. No blocks, no symbols. Oh, actually, that's not true. We started off with like one like this to get the idea of it, what I'm doing. And then after that, it was, all in his head. Didn't write anything down, didn't have to get the blocks out to do it, just 100% verbal. So here, let's see here, let's get back and forth. So here, there's, there they are set up. There's 28, and one side 7, what's the other side? And then what's the perimeter? Here's a bunch of 8s, and, one side obviously is 8, this side is 6, right? So, if I could tell you that the whole thing is 48 and one side is 8, what's the other side? 6. What's the perimeter? Now we have to do some math in our head, right? Because I have to add these two and add these two, and then add them all, right? So usually what you'll see the kid do is do 16 plus 12, or whatever. Anyway, and then here, this one you'll see we change that around, or I changed it around just to make it easy and fun for you to see. So now you see, oh, this rectangle is the right way now. The whole area is, the area is 6, one side is 2, the other side's 3, perimeter's 10, right? Simple. All of these, super easy. Now, with this kid, like I said, we started here, and we went directly to this kind of problem, where I just said, look, the area is 20, one side's 5, what's the perimeter? So now he has to tell me the other side, and then obviously the perimeter, right? So what kind of problem are we doing? Division, right? And then addition, or multiplication, depending on how he did it in his head. So there's these, right? So there's like the area is 36, one side's 4, and you'll see these on tests all the time, GEDs and SATs and all kind of stuff, right? They give you just this much information, and you're supposed to be able to, it's supposed to be a big deal that you can find the other side and add stuff together. And obviously it's not. And then the next step, like I said, how is it possible that textbooks will say stuff like, a neat trick to check your work is, multiply these two, right? the quotient and the divisor, and you'll know if you got it right or not, or, it's a neat trick to check your work. It's not a neat trick, they're inverse functions. Now, if you spent your whole life, or a whole year of your life, going 3 plus 3, right? 2 3s, 2 times 3 is 6, and 3 6s is 18, and you've never seen that you can make a rectangle out of them and count the sides, then yeah, I can see where, but seriously, can you see when you do conceptual math that you can't possibly get away with teaching multiplication without getting some division in there, and vice versa? If you're going to teach division, you're going to see the multiplication. So, and also, the other thing is, this right here is shorthand for rectangle. Right? Many people are always amazed by this. This is shorthand for rectangle. If I build a rectangle like this, the whole thing's 18, one side's 3, the other side's 6. Erase this, and it's a division problem, obviously. Easy. How fun is that? And any little kid can do this. Little kids, this is where you start, right? If you've got a 5-year-old, well, maybe you don't start on big ones like this. You start on little ones like this, where you give them the whole thing, and all they got to do is you tell them, look, this is 6. Tell me the sides, and they'll be able to tell you one side's 3, the other side's 2. Look, this is 20, right? And I've got a couple 5-year-olds, or 4 and a 5-year-old, that can do this problem right here because they can count by 4s all the way to 28 easily. And they could do this one too because they can count by 4s all the way to 36, right? Easily. And they could probably do this one too because they're getting pretty good at counting by 6s. Again, you start here and move here. And when they're 4 and 5, they have no interest in ASSP. Right? So what you do, start here, move to these symbols, and you could also do it where you show this side and that side and it's multiplication, or you show the whole thing, right, and they count one side and they have to tell you the other side, and it's division. Makes it simple and easy. Anyway, Crewton Ramone's House of Math.com for more.